Good afternoon, everyone. I am Mujibur Rahman. So I will be taking the session 4 for the advanced soil mechanics problem solving sessions. So this course is being taught by Professor Srideep Sekran from the Department of Civil Engineering, IIT Guwahati, and I am from the Department of Civil Engineering, IIT Madras. So in the last session, in the last week, you have went through the you went through the basics of shear strength of soils, what it is, how we define the shear strength, and what are the failure criteria based on which we will say whether the soil is failed or not, and what are the different criteria, whether it is Mohr Coulomb or Coulomb's model. Then after that, you have went through the shear strength behavior, or how the shear strength or the shear response of soil varies in cohesionless soils and then the cohesive soils. I will go through that briefly. After that, we can have the numericals, or we can have some problem sessions. So we'll start with some basics. Shear strength of cohesionless and cohesive soils, which is the topic that has been taught in the week 4. So in this week, the professor started with the basics of shear strength. Correct. So what the shear strength is? So actually, we know that if a sample is being subjected to the all-round stresses, all-round equal stresses, that is not going to shear the sample. It's as simple as we call it consolidation, where we are applying the equal stresses on all sides of the sample. Then we are allowing the sample to change the volume. So as you can recollect from the previous lectures, that there are two things. One is the volume change behavior and the shear strength, where we are decoupling them. So this consolidation brings, or this R-round equal stress are actually doing the volume change. They are bringing the volume change in the sample, and when we are doing the unequal loading, that is actually inducing the stresses in the sample. That's why I have written that unequal loading induces shear stresses and cause particle slippage, and this particle slippage will cause the soil to fail. Now, what is shear strength? How we define the shear strength? It has been defined as a limiting value of the shear stress that the soil can withstand with reference to the failure plane. So it's actually the limiting value. It is the limit up to which a soil can hold the stresses. After that, if we lower the sample or lower the soil, it's going to fail. So please note that this shear strength is always associated with a failure plane. Now, how we are defining the failure in this? How we can say whether the sample has reached the failure or not? For that, we have the two criteria. Initially we have two, then we have the modified one, which is the Mohr Coulomb. So we'll start with the Coulomb frictional model, which is actually given by equation tau f is equal to sigma f dash tan of phi dash, where sigma f is the normal stress acting on the failure plane, and this tau f is the shear stress acting on the principal plane. Since the pore water pressure doesn't have any effect on the shear stress, that's why we are written in terms of a total stress parameter. But this normal stress, it has the effect of the pore water pressure. That's why it's in terms of effective parameters. Now it has been extended for the cementing soils, where the cementation can be a true cementation or apparent cohesion, true cementation or the apparent cohesion. It's for the cementing soils, and for that, this extended Coulomb friction model can be used, which is given by tau f is equal to c dash plus sigma dash tan of phi dash. Fine. Now, based on if the sample is being subjected to the two principal stresses in the lateral direction and the vertical direction, and we are supposed to determine the failure stresses at a plane which is inclined to theta with respect to the horizontal. So it's given by sigma f dash is equal to sigma 1 dash plus sigma 3 dash by 2 plus sigma 1 dash minus sigma 3 by 2 cos of 2 theta, and tau f, which is the failure shear stress, given by sigma 1 dash minus sigma 3 dash divided by 2 sine of 2 theta, where theta is 45 plus 5 by 2. Now after that, we have gone through the Mohr Coulomb failure criteria, which is a modified one and is most widely used. So according to the Mohr Coulomb failure criteria, it's telling that the failure occurs when the Mohr circle touches the failure line. It means that the soil will fail only if this Mohr circle, which is actually the that we get from the triaxial tests, at the point when this Mohr circle touches the failure line, we are telling the soil has been failed. and the equation is given by sigma 1 dash is equal to sigma 3 dash tan square 45 plus 5 by 2 plus 2c tan of 45 plus 5 by 2, and the sigma 1 dash by sigma 3 dash is called the stress obliquity. And as per the Mohr-Coulomb criteria, failure occurs on maximum obliquity. Yeah, that means sigma 1 dash divided by sigma 3 dash is achieved, that's at failure, and not when the maximum principal stress is achieved. It means that you can see that this maximum shear stress, it's around here. So you can see that this is well below the failure line. So it means that the failure in the sample will occur only when we have a critical combination of stresses, which is given by the sigma 1 dash divided by sigma 3 dash at failure, and this is it is a maximum value at the failure. Now after that we have the different stress representations, how we are representing the stresses. The first thing that we have went through is the Cambridge plot, which is given by Q to P dash, QP dash plot. How we are defining the Q and how we are defining the P. First we will go through that. For example, if you have a sample and you have axial load sigma A dash, or axial stress acting on it sigma A dash, and the radial stress acting in sigma R dash, and in the triaxial condition, generally this, if we talk about the compression case, the sigma 1 will be acting in the vertical direction and the sigma 3 will be acting in the radial direction. It's a true it's a triaxial condition. Now how we define the P dash, which is a mean effective stress given by sigma A dash plus twice sigma R dash divided by 3. Now in the compression case, while you are doing the compression on the sample, the sigma A will be equivalent to the vertical stress, which is sigma 1 dash plus 2 times the radial stress, that is given by sigma 3 dash. And so the formulation of P dash will be sigma 1 dash plus twice sigma 3 divided by 3. And for the Q, which is the derivative stress given by sigma A dash minus sigma R dash, where sigma in case of compression, this sigma 1 dash will be the vertical stresses acting on the sample, and sigma 3 is the radial stresses. And in the QP plot, if we draw the failure line, which is given by KF, which has the equation Q by P dash, the slope of the line is Q by P dash given by 6 times sine phi dash divided by 3 minus sine phi dash, and this is for the compression. Now another way of representing this is TS dash plot, which is called the MIT plot, or maximum shear stress plot, in which we are using the two parameters S dash given by the sigma A dash plus sigma R dash by 2, and T dash, which is given by sigma A dash minus sigma R dash by 2. They are actually the center and the maximum shear stress of the Mohr circle. If we draw the Mohr circle, you can see that this point is actually T and this is actually S, correct? Now the modified failure envelope as per the definitions of T and S is given by T is equal to A dash plus S dash tan of alpha. And after doing the calculations and all, we have seen that this tan alpha is equal to sine of phi dash, and C dash is equal to A dash divided by cos of phi dash. It means that from the these are interrelated, this MIT plot and Cambridge plot, they are interrelated, and if we know one parameter from the this QP plot, we can get the parameters for this MIT plot. Now we will move towards the shear strength of granular soils. Now we know that granular soils, generally we refer to the cohesionless soils which have less or no clay content, correct? So there will be no cohesion between the particles. You can see there is the sand are there, gravels are there, so they are the cohesionless soils. Now how they are responding to the shearing? Now depending upon the state, what the state of the soil is it in a loose state or dense state? And for the cohesionless soils, how we are determine whether the sample is loose or dense, it depends upon the relative density of the sample. The chart which has been shown in the during the lectures, where the professor show you that based on the relative density, how we are defining the sample will be a loose or dense. Now depending upon the initial state of the soil, whether it is a loose or dense, the response of the soil changes. Now if we see, we have a this test from the results are from the direct shear test, but behavior used to be same whether it is from the direct shear test or the triaxial test, because the response of the soil will be same. Now you can see that for a dense sand while we are shearing it, it will achieve the peak quickly, and after achieving the peak, the stresses will start to decrease. It goes down until it achieves the final state that we call the critical state. And this, after the peak, the decrease or the decrease in the stress value, we call it's softening. So we can say for the dense dense cohesionless soils or dense soils or dense granular soils, they are having there is a well-defined peak. They are achieving a well-defined peak, and after they are achieving the peak, they are undergoing softening till they reach the critical state at maybe a large range. Similarly, for the medium dense, which is showing the similar behavior between the between the dense and loose, and for loose you can see there is a continuous hardening, which means that there is no peak, and this behavior continues till the loose sand will achieve the critical state. So irrespective of the soil type, whether it is loose or dense, during sharing or during sharing the sample at large range, the sample is reaching the critical state, which is the final state which a sample can achieve. So this is the tau critical or critical shear strength. Now this, what happens in loose case, why the behavior is like this? Actually in loose state, the soil particles are moving horizontally, and they are moving horizontally and getting packed into a dense configuration. I mean to say that during sharing there is a particle arrangement which is actually increasing the strength, reducing the void spaces, and they are moving horizontally as you have seen in the lectures also, how they are being packed. So they are going horizontally and getting packed in the void spaces. So they can be better modeled by the Coulomb's friction model given by sigma f, tau f is equal to sigma dash f tan of phi. In case of dense state, what is happening that the soil particles are moving upwards. Let me show you. Can see particles, dense particles like this. When you shear them, they are going like this. It means that the particles of the dense sand, what they are doing, they are actually moving upwards during the shearing, and which can be idealized by a block moving up the inclined plane. Fine. And the equation, failure equation, or the how we relate the stresses, they are related by equation tau f is equal to sigma dash f tan of phi dash plus alpha. What is alpha? Alpha is actually the dilation angle, and I mean to say this dilation angle, it's actually the how much the sample can dilate given by the alpha, and with the increase in the normal stresses, with the increase in the sigma dash f, this dilation will decrease, because particles will not have a much freedom to allow to do the volume change. Now this, as we increase this alpha, the frictional resistance will increase, and we can relate this peak, this tau, the friction angle corresponding to the peak. It has a relation with the friction angle corresponding to the ultimate, corresponding to the critical state, and this dilation given by phi peak is equal to phi u plus alpha. So this we are using in the soil mechanics for determining the peak friction angle critical or the dilation angle. Correct. Now we will show that after that we saw that how the dilation angle or the dense, how the Mohr Coulomb failure in the envelope is getting affected by this dilation. You can see this is the Coulomb friction line, which is without dilation. There is no dilation. This can probably for it's a loose sand, but once the dilation comes into the picture, you can see there is a curvilinear stress, this failure line. So it means that this shows the effect of the normal stress on the alpha. We can see that for let's assume that at this sigma 1, the peak value is tau peak 1, and when we are increasing the stresses to sigma 2f, so the peak value is tau peak, and this is the point where there is no dilation, and the sample will follow the normal Coulomb's failure line without dilation. It means that as we are increasing the normal stresses or normal stress on the sample, this dilation angle is getting reduced. So this causes the failure envelope to be curved or non-linear, and alpha, the dilation, is a measure of volumetric strain, change in the volume with respect to the change in the shear strain. And some formulations for the tau peak given by sigma dash tan of phi dash plus alpha, because here it should be at phi of peak, which is given by phi dash plus phi dash u plus alpha, and at the critical state we have the tau critical state is equal to sigma dash f tan of phi dash critical state, and it's a well-known equation given by Bolton. Phi dash peak is equal to phi dash critical state plus 0.8 times alpha, and this is for the plane strain case. Now, since I talked about this state, critical state, like whatever be the soil, whatever be the state of the soil when you are sharing it, when you are sharing the sample, it will achieve the critical state, which is the final state a soil can achieve. Now let's have a brief look at what the state is. For example, if we have a loose sand which have a void ratio much higher than the critical state, when we are going to shear it, what is happening, or when we are going to shear it, what is happening, its void ratio will decrease. It will start, it's like we are compressing the sample, and when we are reducing the compression of the sample, means the void ratio is getting reduced. So this void ratio will start reduce till it reaches the final value, which when it reaches the critical state. That is called the void ratio corresponding to the critical state is called the critical void ratio, EC. And similarly for the dense sand, what is happening that it will have void ratio less than the critical state, correct? And when we are sharing it, there will be the dilation, or there will be the increase in the void ratio due to the dilation till it reaches the critical state. Once it reaches the critical state, there will be no further change in the void ratio. So this critical critical void ratio, it's actually independent of the initial state of the soil. Now, it was Cassagrande who proposed this a critical void ratio line for separating the soil which will undergo the liquefaction or which will not undergo the liquefaction. For example, this severe line we have, it is the plot is between the void ratio versus the effective, the confining stress, or we can say sigma dash C. Now this is the severe line, critical void ratio line. Now if we have this loose soil is there, and it has to reach a critical state. Now we have the two tests, we have the drain test and undrained test. Now during the drain test, it will undergo the compression. Fine, it will undergo the compression, it will reduce the void ratio till it reaches the critical state. Now for the same loose soil, if we are doing the undrained sharing, where we are not allowing any kind of volume change, what will happen? The mean effective stress of the sample will reduce, so much that this state of the soil will reach to the critical state. It means that during drain E is changing, and during the undrained sharing, the sigma mean effective stress or the P dash is changing till it reaches to the critical state. But what happens for the dense soil? In the drain case, what is happening? As you saw here, the drain case, there will be the dilation which will increase the void ratio till it will reach to the critical void ratio line. And in the undrained state, what will happen? That there will be the increase in the mean effective stress until it reaches the critical state. And this observations are very helpful in understanding the shear response of granular soils, for cohesionless soils, and also for understanding the liquefaction aspects of the different soils. The severe line describes the state towards which the soil specimen would change at last change, and this change can be either by the change in the volume, as I show you in the drain case, there will be change in the volume, because delta V will be proportional to the delta E. Whatever be the volume change, it will be proportional to the change in the void ratio, or it can be achieved in the undrained condition by the sigma dash C, by increasing the sigma dash C, by reducing the mean effective stress, or by increasing the mean effective stress. Or in case of partially drained specimens, it can happen in both ways, either by delta V change in the volume, or by increasing or decreasing the mean effective stress. Now it was for this whole story of shear strength and all, it was for the cohesionless soils, correct? Now how the things will go for the cohesive soils, which have some kind of cementation also, and the behavior on the response of the soil depends upon the it's depending on different factors like the drainage condition, stress history, loading condition, initial condition, type of the test. Now before going to the sharing part, we will first see the volume change characteristics of cohesive soils. So this is a E versus log sigma curve for the cohesionless soils, that one can either achieve it by a consolidation or by the triaxial test also. So AH is actually the normal consolidation line. The slope of which is given by Cc, correct? And this NCL, if the soil is following the NCL, it means that this state of stress the soil is achieving at the first time, and the behavior it will show is elastoplastic, correct? Now, during the loading, when we are loading the sample, sharing the sample, at some point of time, let's assume B, we are telling the sample, okay, stop, we are now to the unloading part, and we are allowing the sample to unload from B to C. And during this part, since whatever the load will come in this portion B to C, correct, it will be less than what the soil has achieved at point B. It means that, what it means? It means that there will be kind of a stress relaxation. The stress will become reduced because it has achieved it had already gone through a stress of sigma dash B in the past. Now we are giving a stress which is less than the sigma dash B. So now the behavior of the soil, it will be kind of a it will be in a OC state, correct? So the behavior in this BC part, it will be a elastic, correct? Now after again when we load this sample from C to B, since it will be a kind of elastic, it's an elastic deformation, so it will follow the same path from C to B. And once we start loading the sample at a stress higher than B, it will again follow the same AH line, and the behavior will be elastoplastic behavior. And this stress is that this sigma dash B, it's called the yielding stress. It's called the yielding stress. Now, for example, if we take another point, if we take point here and start unloading here, if we start unloading here, again it will follow some path. Let's assume it is G here, it is P here, correct? It will take here, it will go here and come back. Now this G, the stress corresponding to G, sigma dash G, will be the new yield stress for the soil. So this yield stress, it's not a constant term. It's a function of the stress, or we can say it's a function of the loading. Fine. So this yielding, so it means that this yield stress is not the constant value for the soil. It's actually changing. It depends upon the stress history. So what are the takeaways from this? We will say that this normally consolidation, if a soil is following the normally consolidation, then the stress state that the soil will be achieving will be the current stresses will be the higher than the previous stresses. And if the stress that a soil is experiencing is less than what it has experienced in the past, it will follow the BC route. We can say this, the behavior of the soil will be overly consolidated. This is the overly consolidated soil, and the AH will have a normally consolidated soil. Now, depending upon whether the soil is OC or NC, we can have a different behavior of the soil. So now, if we see the sharing behavior of the OC, NC, and LOC, it's lightly overly consolidated. Its behavior will be similar to the cohesionless soils. Now, the way we are defined will be different. Like we have the loose state here, we can say normally consolidated. So again, for over consolidated clays, we can see there is a well-defined peak. After the peak, there will be stream softening, usually followed by the critical state at the large streams. Similarly, for the NC, what will happen for the normally consolidated soils? There is a like continuous sharing, continuous stress is getting developed in the sample, and we call this strain hardening until this behavior like it will progress till it reaches the critical state. Now, for lightly overly consolidated, it is between the OC and NC, and the mechanism that governs the behavior of OC and NC is same to the loose and N states. Now, if we talk about the volume change, how the volume change will occur in the NC, LOC, and OC. We can see that delta V is the volume, that's the change in volume, and is the strain. You can see the NC, there's a continuous compression of the sample, because it is the stresses that the sample is experiencing for the first time. It will be more than the what it has experienced in the past. So there will be the new readjustments in the soil sample, correct? So there will be a continuous compression. But in case of OC soil, since it is like in a very high packing state, and the current stress are less than what it has experienced in the past, so what will happen that it is actually showing the dilative behavior, right? Initial compression followed by a dilation, and this behavior of LOC is somewhat between the OC and NC, but you can see there is a initial part of compression and then a dilation, correct? So this was the overall summary of the overall summary of the I mean to say what has been taught in the session 4, which has discussed, in which the professor had discussed about the basics of shear strength, started with the definition of shear strength, then how we are defining the failure, whether it will be the Coulomb friction model, extend the Coulomb friction model for cementing soils, then the Mohr-Coulomb friction model. After that, how we are representing the stress state. It can be either by Cambridge plot or the MIT plot, and then the shear strength of granular soils, the shear strain response of sand, how the behavior of loose state is different from the dense state, and after that how dilation comes into picture, and how we are actually determining the dilation of the sample, and how this dilation is affecting the volumetric response, and also the effect of the normal stresses on the dilation. Then we related the peak, then we determine the peaks, tau f, peaks shear stress and critical shear stress, and after that we have discussed the critical void ratio, which is the final void ratio which the soil can achieve irrespective of the initial state. Whatever be the initial state of the soil, if we shear it, it will start reducing the either it will reduce or it will increase to reach the critical state. Now after that we discussed the critical void ratio line, which was given by Casagrande. This is useful for the study of liquefaction and also to study the different behavior of the cohesionless soils, or even for the for loose and dense soils. And CVR, it describes the state towards which the soil sample can change. Either this loose state can achieve the critical void ratio in drain condition by changing the volume, or it can reach the critical void ratio by changing the stresses, mean effective stress. Similar, same is true for the undrained case. In the undrained, for the dense state, for the dense soil can either reach the critical state either by drain condition, which means that there is a volume change, and in the undrained condition it can reach the critical state by increasing the effective stresses, mean effective stress. After that, we went through the shear strength of cohesive soils. We discussed that the shear strength of cohesive soils depends on the drainage conditions, stress history, loading condition, initial condition, and type of the test. After that, we went through the volumetric response or the volume change characteristics of cohesionless soils. This test we show that what is the NCF, normal consolidation line, how the behavior of the soil will be there. It will be elastoplastic, and then we went through the shear response of the soil, of the cohesive soil. Now we will try to solve some problems. Fine. So problem first, it's related to the stresses, for finding the stresses and strains. So it's question first. So you have a sample, triaxial sample, in which the axial or the vertical stress acting is 52 kPa, and the sigma 3 radial stress acting is 12 kPa. Now you have been asked to find the sigma f and tau f, which is like the failure. What is the failure normal stress and failure shear stress on the plane which is inclined at 35 degrees from the horizontal, right? So there are two ways to do it. Either you can use the Mohr circle, like you have been given sigma 1, which is the 52 kPa, and sigma 3 is equivalent to 20 kPa, and theta has been given to you. Theta is equivalent to 35 degrees. So there are two ways. I told you there are two. Either you can use the Mohr circle for determining the sigma f and tau f. How? We know that for a Mohr circle, what the two things we need? We need a radius and the center of the Mohr circle for plotting it. For example, the sigma and tau, correct? So in order to draw a Mohr circle based on this condition, we need a center. So we know that center of the Mohr circle is given by the average of these two. So the center of the Mohr circle will be, I can write here, center of Mohr circle is given by sigma 1 plus sigma 3 by 2, which is equivalent to 52 plus 12 divided by 2. So it will be equivalent to, using the calculator you can also use, 52 plus 12 by 2 is equivalent to 32, correct. So 32 kPa, and it means the center is from the origin, the center is here, 32 kPa, correct. This is the origin. Now if we know the center, if we also know the radius of the Mohr circle, so the radius of Mohr circle is it's given by sigma 1 minus sigma r divided by, sorry, it's sigma 3. What is sigma 1? 52. Sigma 1 is 52, and sigma 3 is 12 divided by 2. So can you calculate it? 52 minus 12 divided by 2, it's 20. Okay, so it means that, let me try it roughly, somewhat like this. So this will be sigma 1, this is sigma 3, correct. Now we know about the term, that's the pole of the Mohr circle, which is actually the point. If we draw a line through the pole at the same inclination, first determine the pole is important. Let me show. See, the pole is actually the point on the Mohr circle. If you draw a line through a pole and at the same inclination to what the inclination has been given here, you will get it will intersect the Mohr circle at a point. That point will give the stress strain corresponding to the failure. So how we are determining the pole? See, you go to this sigma 1. Sigma 1 is actually acting on the horizontal plane, correct. So this means that sigma 1, at I am like representing it here, it's actually the horizontal plane, correct. Sigma 1 is here of value 52. Since there is no shear stress acting on the plane, so it will lie on the sigma plane, correct. So it will be here, correct, and the plane is horizontal, so it will be like this. Now the sigma 3, which is 12 kPa, so I will go from here to 12, which is here. Now the inclination of this plane sigma 3 is at an angle of 90 degrees, correct. So in the Mohr circle we are taking it 2 theta. So if the angle is alpha, so the angle in the Mohr circle will be 2 alpha. So it is 90 into 2 is 180. So 180 we have to draw from the, or we can say instead of this sigma 3 is acting at 90 degrees to it. So we can simply draw a 90 degree plane here. So the intersection of these two planes, one plane is the horizontal plane on which sigma 1 is acting, and the plane through the sigma 3 at which the sigma 3 is acting. So intersection of these two planes will give the pole. Now if we draw any line through this pole at an inclination of 85 degrees, that will actually give the stress state. So if you draw the line, it's like this, fine. So this is actually the, let's call it by A. So the coordinates of A, sigma f will be sigma f and tau. So this will be the sigma f, and this will be the tau, correct. Not a tau f dash, but tau. Now either you can do it by this way, or like a geometrical way, or we have the equations, correct. So we have determined the equations earlier, and I will show you. Yeah, these two equations, sigma f dash is equal to sigma 1 dash plus sigma 3 dash by 2 plus sigma 1 dash minus sigma 3 dash by 2 cos of 2 theta, and here we can just write this dash, right. So tau f is equal to sigma 1 dash minus sigma 3 dash divided by 2 sine of 2 theta, correct. So we'll use these equations if we don't want to do it like using the geometry and all. So from the, if we solve it, so what will be this sigma f? Sigma f will be equal to, as I shown you, sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos of 2 theta, and tau f will be sigma 1 minus sigma 3 divided by 2 sine of 2 theta. So what is theta? Theta here is 35 degrees, and sigma 1 is 52 kPa, and sigma 3 is 12 kPa. Therefore sigma f will be 52 plus 12 by 2 plus 52 sorry 52 minus 12 by 2. 2 theta means 70 degrees, correct? So can you calculate? So I am using calculator. 52 plus 12 by 2 plus 52 minus 12 by 2 to cos of 70 degrees. It's coming out to be 38.84 kPa. Now tau f, sigma 1 minus sigma 3 divided by 2 sine of 2 theta. What is sigma 1? Sigma 1 is 52 minus 12 divided by 2 sine of 70 degrees. Sorry. So 52 minus 12 by 2 into sine of 70 degrees. So it is 18.79 kPa. So it means that this ordinate here is 38.84, or we can say it's 39, and this we can, so it's 90 degree here, it's kPa, right? So it means that this ordinate is 39 and this ordinate is 90, correct? So this I show the both ways, one is the geometrical way and another is the using the equations that we have formulated from the geometry only. So both are correct. Now we have another question here. It's asking that a dry sand was tested in a shear device. Okay, we have a dry sand that we have tested in the shear device, and the shear force displacement for a normal force of 100 kPa is shown. So it means it's a direct shear test where we have applied the 100 Newton of say a load at the top, and then we are doing the shear displacement on the sample. So we have got the shear response and shear displacement plot for 100 kPa of normal force. Now the first question that is being asked is the soil a dense or loose state, or is the sample loose or dense? The second question is determine the peak shear force and the critical state shear stresses. So these we have to determine the peak shear force and the critical state shear force, and also the part C, which is asking to calculate the peak and critical state friction angle and the peak dilation angle using the Cohesionless model. The first thing, if we look at this plot, when we are sharing the sample, what is happening? There is an initial increase in the response, and once it has achieved the peak, the displacement, the shear response of the soil is decreasing, and then it has reached the critical state. It means that after achieving the peak, it has undergone softening. So this is the critical or the behavior that the dense sand uses. So we can say, is the soil a loose or dense? We can say it's a dense sand because it has a well-defined peak followed by a strange softening till it reaches the critical state. So here I can write it's a dense sand. Correct? Now the second part, it's asking determine the peak shear force and the critical state shear force. Now we have to understand why these points lie. See, the peak shear force means the shear force corresponds to the peak state that the soil has achieved. So this is the peak stresses or the peak state that the soil has achieved, and the shear stress corresponding to this will be the peak shear force. Correct? Now what is the critical state? Critical state is it's generally occurs a large strain greater than 10, and after in this critical state there is no change in the shear force. The variation of the shear force will be constant. Correct? So we can see that it has achieved this critical shear stress in this portion, where the critical shear force is critical state shear force is equivalent to 57. So we can write for B sorry, so I can show it by point A, and I will note this critical state by point B, correct? So why? So A corresponds to peak state and B corresponds to the critical state. Therefore, what has been asked, determine the peak shear force. So I can see Px peak shear force is given by 78 Newton, because the peak state stress corresponds to A, which means it's equal to 78. And now the Px in critical state. So what is the Px in critical state? The stress corresponds to state of the soil at B, which is 57 Newton. Fine. Now what is the PZ is 100 Newton that has been applied. So why Px? Because during the shear work test we are applying the shear in the horizontal direction, correct? That's why it's like this. Else we can show it by some other I would say by some other alphabets or some other I would say by some other symbols also. So this is the critical and peak shear stress. Fine. So now part C. Calculate the peak and critical state friction angles and peak dilation angle using the Coulomb's law. Now we know that for determining the peak and critical state friction angle, we should have the formulation tau f is equal to sigma m dash tan of. This is the general failure equation, correct? Like use it as per the Coulomb's model. Now if we use this equation for the peak, right? So for the peak we will have tau f peak is equal to sigma f dash into tan of phi peak. This sigma f dash is 100 Newton here, and this tau f is 78 at the peak. So this phi dash p will be equal to tan inverse of tau f at p divided by sigma, correct? So we'll get, can we do it? Tan inverse of tau, tan inverse of 78 by 100, correct? So 78 by 100, it's equivalent to around 38 degrees, correct? Now what is the now we have to determine the dilation angle also. So similarly for the dilation, I would say we will first determine the critical state, because phi peak and phi critical has phi critical and the phi peak has a relation with the dilation angle. That's phi peak is equal to phi critical state plus alpha. Alpha is the dilation angle, correct? So we will now determine the phi correspond to the critical state. So phi dash critical state will be equal to similar to this equation, tan inverse of what is the shear stress corresponding to the critical state, which is 57 divided by 100. So can you determine what is the tan inverse of 57 divided by 100? So which is equivalent to 29.7 degrees, correct? Now we have the both. We have phi p, we have phi critical state. Now what is the dilation angle? We will use the equation as per the Coulomb's, that is phi p dash is equal to phi dash critical state plus alpha, and implies this alpha will be equivalent to phi dash p minus phi dash critical state. So what is it? Is 38 degrees minus 29.7 degrees. It will be equivalent to 8 point. What is it will be 8 point this minus 29.7. Yeah, 8.3 degrees. So dilation angle will be, dilation angle is equivalent to 8.3 degrees, correct? So all the parameters have been determined now. We have the dilation angle, we have the peak state friction angle, critical state friction angle, we have the peak shear force, the critical state shear force, correct? So this is the way how we have determined the peak dilation angle using the Coulomb friction model. Correct? Now we have another question. A cylindrical soil sample was subject to a axial principal stress sigma 1 dash. So we have cylindrical sample in which in which the axial principal stress is sigma 1 dash and the radial stresses are sigma 3 dash. Correct? The soil could not support additional stress when sigma 1 is equivalent to 300 kPa and sigma 3 dash is equivalent to 100 kPa. Okay, so it means that we have been given the sigma f1 at failure also and sigma 3 at failure also. So it is 300 and 100. So this is 300 kPa and this is 100 kPa. Correct? Now determine the friction angle and the inclination of the slip plane to the horizontal. So we have been asked to determine the friction angle and also the inclination of the slip plane to the horizontal. Now for determining this the friction angle, we know the equation sine of phi dash is equivalent to sigma 1 dash at failure minus sigma 3 dash at failure divided by sigma 1 dash at failure plus sigma 3 dash at failure. So can you put this? So can you put the values in the equation? So 300 minus 100 divided by 300 plus 100. So which is equivalent to 1 by 2. So sine of phi dash is equivalent to 1 by 2. So phi dash is equal to sine inverse of 1 by 2. It's equivalent to 30 degrees. Now we have been asked to find the inclination of the slip plane to the horizon, which means that we have been asked to determine the theta. So theta is equal to 45 plus 5 by 2. It's 45 plus 5 is 30 divided by 2, which is 45 plus 50. It's 60 degrees. So the friction angle comes out to be 30 degrees and the theta, which is the inclination of the slip plane to the horizontal, it is 60 degrees. Correct? Now we have the last question, which is question 4. After that we will have a discussion or the doubt sessions. If you have any doubt or regarding this week 3 content or sorry week 4 content, you can ask. So I will go through the question. So figure 1 shows the soil profile at a site for a proposed building. Determine the increasing vertical effective stress at which a soil element at a depth of 3 meter under the center of the building will fail if the increase in lateral effective stress is 40% of the increase in the vertical effective stress. Okay, and K naught condition is given. K naught at K naught condition is being prevailed because as the K naught is given as 0.5. The soil the soil sample or the profile is being here. It is the ground level. Fine, ground level is here and the soil element is here and the gamma set of the soil is 18 kPa and critical state friction angle given as 30 degrees. So what is happening that due to the increase in vertical effective stress at which the soil element okay, we have been asked to determine the increasing vertical stresses at which the soil will fail, and once this soil will have this increase in vertical stress, like it will have some initial stress, then due to the increase in the the vertical stress, there will be the failure in the sample. Now corresponding to this increase in the vertical stress, there is an increase in the lateral stress also, that is given as 40% of the increase in the vertical stress, vertical effective stresses. So based on these two statements, we have been asked to determine the increase in vertical stress, how much the stresses have been increased, so that there is an increase in 40% of increase in the lateral stresses, and as a result of which there is a failure. And one more important point, that is that like the soil element is at the center of the building. Correct? So if for example the building is here, it corresponds to the center of the building. It's for actually if the soil element is laid far from here, then the stress distribution will have to take part. So since this is completely under it, we can similarly use the relationships. The first and foremost thing, what do you think? How should we approach this condition? So first of all, we will determine what are the initial stresses initial stress is like acting on the soil element. Let's call it P. Correct. So we will assume this top layer is saturated. Correct. There is no capillary action of water. So based on that, what are the effective stresses? Sigma are not acting at point B, which is at a depth of 3 meter, which will be equivalent to 18 is the saturated weight into 3 minus 2 into what is the level of water? 2 into gamma W is 9.8. Correct. So these are the effective vertical stresses or the initial effective stresses which are acting at point B. So this is equivalent to 34.4 kPa. Fine. Now this before building or before increasing the vertical stress, this was the initial vertical stress. Correct. So we can consider this at this sigma z naught dash is equivalent to sigma 1 dash. Correct. At the initial point of time, this was the effective stress or the vertical effective stress acting on the soil. Now corresponding this sigma 1, what are the later stresses? Sigma 3 dash can be is equivalent to k naught times sigma 1 dash. This is the relation that we are using in the active earth pressure or the rest conditions or the later or the passive conditions. K naught times sigma 1. K naught is given as 0.5, so it's half of the 34.4, which is equivalent to 17.2 kPa. So this is the initial state of the soil, sigma 1 dash and sigma 3. Now the question is, there is an increase in the delta sigma 1, and due to this increase there is an increase in delta sigma 3, and this increase is equivalent to 0.4 times 40%, that is 0.4 times of delta sigma 1. So we have to determine this delta sigma 1. And important and another parameter that has been given is the critical state friction angle, that is 30 degrees. So we know the relation, and just now we use that relation. This equation we use now, we will just inverse this. We will keep this sigma in terms of pi. So we will write at failure sigma 1 dash divided by sigma 3 dash at failure is equivalent to 1 plus sin phi dash critical state divided by 1 minus sin phi dash of critical state. So once you solve this, it will be equivalent to 3. Now, correct. Now another thing is there. Can we determine this sigma 1 dash at failure? It's equivalent to initial sigma 1 dash plus delta sigma 1 dash. Correct. Because this delta sigma 1 dash has bring the soil to a failure state. Also sigma 3 dash f, it's equivalent to initial lateral stresses plus change in the delta sigma 3 due to the delta sigma 1. Now this delta sigma 3 has been given. It's been asked, it has been told that it is equivalent to 0.4 times delta sigma 1. So we will write sigma 3 dash plus 0.4 times delta sigma 1. Correct. Also we can write sigma 1 dash failure is equivalent to, what is sigma 1? Sigma 1 is equivalent to the initial vertical effective stresses, which is equivalent to 34.4, then plus delta sigma 1 dash. Correct. Similarly we can write sigma 3 dash f equivalent to sigma 3, which is 17.2 plus 0.4 times delta sigma 1 dash. Now can we put the values of this bracket here? So what we will get? We will get 34.4 plus delta sigma 1 dash divided by 17.2 plus 0.4 delta sigma 1 dash is equivalent to 3. Correct. So once you will solve it, you will get delta sigma 1 dash is equivalent to 84 kPa. Sorry, 86 kPa. Fine. So this amount of increase was there in the vertical stresses, which caused the soil to reach a state where the lateral stresses were 40% of the increase in the vertical stresses, and it will fail, like this will cause a failure in the sample, correct? So these were few problems or the examples that I have discussed with you. Of similar concepts you can use for solving the assignments and also for solving the questions in other textbooks. So now I would like that if there is any doubt, you can ask. So I will wait for 5 minutes. In case you don't have any doubt, you can text your questions in the form where we will be continuously observing the doubts asked by the students, and we can just get back to you as soon as possible. So I will wait for 2 minutes. Okay, we'll catch your doubts in the form. So I will conclude today's session here. So let's meet. I think I have next I have next session on next Saturday. So we'll meet on next Saturday. Till then, goodbye.